So what I want to do today is I want to discuss the transformer first, and then I'll go back and do two examples on AC circuits. One is in your notes, and one is your homework problem. That's a little challenging, so I thought I'd get you started on it. Then I'll do that, and then possibly start in chapter 34. Meeting I was supposed to have on Wednesday got canceled, but I think what I'll do is I'll still give you guys the link to Tuesday's class. So if you want to attend the Tuesday one, that's fine. Okay, you guys, if I give you the Tuesday link, would you attend or?
What time is it on Tuesday?
I'm sorry, I didn't hear you.
What time is it on Tuesday? 'Cause
11.
I wouldn't be able to attend, but I would watch the video if it's
Okay. Well, I'll just give you guys a link, and if you want to attend it, that's fine. Otherwise, I'll finish the class up on Wednesday then. I'll give you guys whatever, your option. Okay?
Yeah, sounds good.
So Friday's exam 5. It's going to be chapters 32 through 34. It'll only have 3 problems. It'll essentially have one problem from 32, one problem from 33, and one problem from 34. Okay?
Are you being merciful, or are they hard questions? Just 3?
I'm hoping I'm merciful. I really think they're going to be very similar to the homework. Most of them, not all of them, right? Most of the problems are very similar to the homework. So really, it would be, great if you make sure you understand how to solve the homework problems that you worked on in the last 3 chapters. Okay? But yeah, they're going to be very similar. Obviously, I might add, I'll add something to it or whatever, but you'll see something similar to them. Okay. It'll have 3 problems and a bunch of not a bunch of short answers, a couple of short answers, because even though there are 3 problems, a lot of them, they have multiple parts. So it'll still be as long as the other exams. But I'm hoping that if you understand how to do the homework problems, that you'll do well on this exam. That's my hope. So make sure, and this always happens on this exam, make sure you know what power factor means. Okay? Because every time I give this test, a test, I ask a question on power factor, and people don't know what it is, even though I discussed it. Okay, so let me begin by briefly talking about the transformer. And I'm going to talk about the transformer, but it's a complicated device. It's used a lot, right? We use it to deliver energy to our homes. Energy is made at the power station, right? Energy is produced at the power station, and it's delivered to your home. And in the process, what's done is the voltage is stepped up to a very high level, and in doing so, the current's decreased. And you do that because you want to reduce I²R losses in the wires. So if you make this smaller, you're going to lose less energy. If you go through Roseville, you see the high voltage wires, right? If you look, there's an area in Roseville where you have energy being delivered over high voltage wires, and it's done so we can reduce power losses. Then when you get to a substation close to your home, the energy the voltages are stepped down so that energy can be delivered into your homes. The transformer, and I have one here, although it's kind of heavy. Let me see if I can. I have it hooked up in a demo. Let's see if I can. I have it on a separate cart. Transformer basically has two coils, and around the coils is an iron core. It is quite complex, and we're going to dramatically simplify the discussion. Its operating principle is based on Faraday's law. Uh-oh. So this is what a transformer looks like, hooked up to a power supply. One of the questions is, how do you model a circuit? Let me ask you guys a question. Can I use a transformer with a battery? Can I use a transformer with a battery?
I would think so.
No, you can't. I mean,
Oh,
I asked that question a lot in an exam. People don't get that. You have to have AC for a transformer, because if you use a battery, you don't have a time varying current. It then means you don't have a time varying magnetic field. Faraday's law says then you're not going to have an induced EMF. So basically you have two coils. Next to each other. You run a current through one of them, and then through mutual inductance, there's going to be an EMF induced in this coil, and then you can hook up a load to it to run whatever. So here you'll have usually we have an iron core. And you actually have to laminate the core to reduce any eddy currents that are actually in the core, because iron's a conductor. And so even if you have a changing flux through here, the iron is going to actually experience an induced EMF. And there's going to be a current in here. And you also want to reduce I squared R here. So you laminate the transformer core to increase R and reduce reduce I and reduce your power losses. So the problem is, how do you model this? It's actually quite hard. Look at how complex this is. Let me make the slide bigger. Look at how complex the analysis is. There's a mutual inductance because of the two coils, but then each coil has a self-inductance, and your load and your source also have an inductance. One can do the analysis. We're not going to do it here. It's quite tedious, but one can do the analysis for this system. But we're going to make some simplifying approximations to make life easy for ourselves. Okay, so we could do a simple analysis. And because transformers can be easily designed so that they're about close to 100% efficient, what we're going to do with the, in terms of the approximations, work out fairly well. Okay. By the way, if the power supply is on this side's called a primary, and this side's called a secondary. Anyway, the side with the power supply is called a primary. And it doesn't matter. I mean, I can switch these two around. If I switch them around, then this becomes the primary and that becomes the secondary. If I put the power supply on the other side for the transformer. So the techniques require some, the analysis requires some complicated techniques, and life becomes more complicated if you take into account the fact that you have an iron core, and if you have eddy losses in your core. So it's not an easy thing to analyze. But we're going to make some simplifying assumptions. We're going to assume that there's no eddy losses in the primary. We're going to assume there's no joule heating. In other words, there's no energy lost because of any resistance in the primary. We're going to assume that whatever flux comes out of here goes straight into here, and the iron core helps to do that. We're going to assume that the impedance on this side is all due to inductance. So the power factor is 0. And that ensures no energy loss on this side. We're going to also assume on the other side that the resistance of the load is much, much less than the impedance of the secondary. And of course, this is an ideal transformer. So this is the ideal case. We're assuming all the flux lines through here go through here. So if I don't have a load here, okay, what will happen is when I have a changing current here, which is going to produce a changing magnetic field, I'll get a small current in the primary that produces a large flux through the core. And so if we have the flux through this side is equal to the flux through that side, then the voltage is only going to be proportional really to the number of turns. This side, the voltage is set by the power supply. Okay, so E1 or V1 is going to be equal to and delta V2 is going to be N2 If you take the ratio of these, the flux cancels. And so the voltages follow this relationship. It's a really simple relationship. The induced EMF on this side depends on the ratio of the number of turns. If this is N1 and this is N2. So delta V2 then is going to be delta V1 times N2 over N1. If the voltage is higher on the secondary, we call it a step-up transformer. So if delta V2 is greater than delta V1, we say it's a step-up. If delta V2 is less than delta V1, we say it's a step-down transformer. Okay? But the transformer, the ideal one, goes by this relationship. So it's a very simple equation. For things to remember, this works by Faraday's law. This analysis is idealized. You can't use a battery with a transformer. Okay? And again, the relationship is very simple. Now, we're going to assume in the ideal case energy is conserved. That means that the delta V on the primary times delta I in the primary has to be equal to delta V in the secondary times I in the secondary. And delta V1 over delta V2 is I2 over I1. And so we can add that to our equation. Questions on this?
I do have a quick question.
Yeah.
We're pretty much only going to deal with ideal transformers, right?
I'm sorry?
We're only going to deal with ideal transformers.
Yeah, we're only
right?
dealing with ideal transformers. The analysis for the secondary, for the real transformer is much more complex. You would probably do it in a electrical engineering course. We're only going to look at the ideal case. So the math is pretty simple.
Okay, thank you.
Now, the current, when I have this set up like this, the current in here is actually quite low. And so let me show you a demo with the transformer. Just give me a second, I got to set it up. I have to move things around. Okay. So what I have here is a transformer. Let me change the view on the screen so you can see everything. My cord's kind of short, so I'm kind of limited. So you guys see the transformer?
Yeah.
And then I have a light bulb. So I have a transformer. I made the number of turns in the primary and the secondary. Let's see, the primary is 250 turns. The secondary is 500 turns. So I'm going to step it up by a factor of 2. So I'll have about 70 volts coming in. I'll get 140 coming out. So let me turn it on. And I have on the primary a light bulb. Hold on a second. I have on the primary a light bulb. And right now it's on. I have no load here. This is open. So I have a very, very small amount of current here. If I close the switch, if I put a load here, then I'm going to have a current in this side, on the other side. Sorry if it's hard to see. I'm going to have a current in the secondary. But that current varies with time. You're going to have a time varying current in the secondary. That means you're going to have a changing magnetic field in the secondary. That's going to want to induce an EMF on the primary, but the voltage on the primary is fixed by the power supply. And so what it does in turn, increases the current in the primary because of Lenz's law. And so when I close a switch, I have a much bigger current. Oops, wrong side. When I close a switch, I have a much bigger current now on the primary side because I have an induced EMF on the secondary. So now it's open. This is not there. Small current on the primary. Close the switch. So I have a load in the secondary. That makes the current in the primary higher. It's an interesting behavior. Questions on that? You'll see that I've discussed very few textbooks, which is surprising. Okay. Now, because of Faraday's law, the current in the primary and the current in the secondary are 180 degrees out of phase because of Lenz's law. Okay? If you actually look on the scope, you'll see that the currents in the primary and secondary are 180 degrees out of phase, and that's due to Lenz's law. Because Lenz's law wants to maintain the flux. Now, since a load produces a current I2 in the secondary, we can find the equivalent resistance of the transformer and load. If I put a load here, I can find the equivalent resistance okay, because I2 is just going to be delta V2 over the load. So let's look at that. The current is going to be delta V2 over the load. If I solve for I1, I get that. And what I want to do is find the equivalent resistance of the transformer and the load on the primary side. And so then I solve this for R equivalent. So I get this result. And then this is just a ratio of the number of turns. And so this is so if you put a load on the secondary side, the equivalent resistance is going to be given by this on the primary side. And if you match that resistance on the primary side, you get maximum energy transfer to the secondary side. All right, we did a problem early in the semester. If you have an internal resistance, if the internal resistance matches the resistance of the load, you get maximum energy transfer. Same thing here. You'll get maximum energy transfer if on the primary side you have a resistance equal to this value. As a result, people use transformers when they use speakers. So you can match resistances from the source to the speaker. So that's really all I wanted to say about the transformer. Because of the fact that we've idealized the transformer, there's not a lot to say. But if you were to do the analysis of the transformer, there's a lot to say. Okay. And it's just a lot of time and tedium. If you're an electrical engineering major, you will spend time in a course doing the detailed analysis of the transformer. So most of the transformer problems you'll see in the book, they're pretty easy. Okay? So I want to do an example. I want to look at a problem. It's not in your notes, but it is one of your homework problems. And I thought I'd go over it because it's somewhat of a challenging problem. But I'm hoping that it helps you to better understand phasors. Suppose I have a circuit with an AC power supply, a capacitor, and then I have a resistor and an inductor in parallel. This is completely different than what we've done so far. This is just an exercise in learning how to draw the phasor diagram. And don't worry, I'm not going to put one this complicated on the exam, okay? All right. How do we analyze this? Well, I got to draw the appropriate phasor diagram. So what do I know? Let's write down what we know from this circuit. We know that delta V sub R is equal to delta V sub L, don't we? And we know that I sub C is equal to I sub R plus I sub L. These are the instantaneous values, right? I mean, I'm applying Kirchhoff's current law, right? Current comes in here and splits. I know that the current through the resistor is in phase with its voltage, with the potential difference across the resistor. I know that the current through the inductor lags voltage, in other words, the potential difference across it, by 90 degrees. But I know that the sum of these two currents has to be equal to the current through the capacitor. I also know that the voltages across the inductor and the resistor are the same. So how do I start drawing my phasor diagram? How do I start drawing that?
Usually start by putting the current straight along the x-axis,
Yeah, in
as
fact,
well as the delta VR.
I'm actually, and the question is which current? I'm actually going to do this one. I mean, I could draw this current, but I want to do this one. I'll show you why in a minute. It'll just make the drawing a little bit easier. So I'm going to draw I sub C. And these two have to equal to this. So I got to form a triangle with I sub C, I sub R, and I sub L, right? These form a triangle because they're like, it's like adding vectors. These two are perpendicular to each other, isn't that true? I sub R and I sub L are perpendicular to each other. They have to be. Because the current through R is in phase with its voltage, and the current through L lags by 90 degrees. That must mean then that these two differ by 90 degrees. So I'm going to draw I sub R and I sub L. And I'll call this angle beta. And this is 90 degrees. And then this is V sub R or V sub L because they're in parallel. They have the same voltage across them. So why did I draw it this way? What if I switch I sub R and I sub L? Why did I have to draw it that way?
Because I sub R is in phase with the VR and VL. Right.
Well, I could have drawn I sub R this way. I mean V sub R this way though. The reason why it's in that order because I sub L has to be behind V sub L by 90 degrees. If I switch them around, that wouldn't be the case. Okay, so what's missing here?
Did you cross the capacitor?
Yeah, and it's 90 degrees behind this, right? So it would be this way, right? But I don't want to draw with the I want to draw with the V's. And so V sub C, something like this. So here's your V's. And so I'm going to complete the triangle. Here's my phase angle. That's my phasor diagram for this system. Now, be honest with you, this is probably not the way you want to solve the problem. I mean, when you take engineering 17, you're not going to do it this way. You're not going to draw a diagram. You're going to be using phasors, but what you mean by phasors, you're going to write it in terms of a complex number. It'll be much easier to do it this way than writing diagram. Okay. But this gives you an idea of how the phasors work. And the more complicated the circuit gets, the less useful this method is.
Professor?
Yeah.
Are you able to explain again why you put VC at the end of VR?
Well, I mean, I want to add the voltages together, right?
Oh, okay. So you just okay, that makes sense. But you
It's a little bit
could've
hard
put
to
it
hear you.
technically
I'm
at the
sorry.
origin and then.
I'm sorry?
So you could have put it at the origin, and then when you wanted to solve for VS, you just do tail to tip.
Yeah, because I want to add the vectors, right? Because I can slide the vectors. When I add vectors, I can slide them anywhere, right?
Yeah.
But so I want to put it here instead of over here because that wouldn't help me. I mean, I could, right? I can put it here, but then if I want to add them, I gotta copy it here.
Okay. Thank you.
So this is 90. This is 90 minus beta. I'm trying to get all the angles in. Now, if I want to figure things out, now I have to do some trigonometry. For example, if we look at V sub s cosine alpha, phi, that's this guy, right? That's got to be equal to V sub r cosine beta. Now V sub s sine of, which is this, this can also be written as this guy minus that guy. Now, tangent of beta is going to be opposite over adjacent. So if I know R and L, which is usually given, and you know omega, you can solve for beta. What else can I figure out? Well, this is 90 degrees. So this is 90 minus phi. This is 90 minus beta. So isn't v sub s squared, I'm going to use the law of cosines, isn't v sub s squared equal to Isn't that true? And this is just going to be and this is just a sine of beta. You know the angle, you know beta. So I'm trying to write down everything I know. I also know that from this phasor diagram. So if you solve, or if you relate v sub s to I sub c, then you can get z. And once you know z, you know most of the problem already. So you can figure out z. You can write an equation for z for this problem. Any questions on this?
I'm having a little trouble overcoming the blur on the left side. What is the subscript on your third equation down?
This one is I
Yes.
sub r equals I sub c cosine beta. Let me write it up here. Is that easier to see?
A lot, yeah. Thank you.
Okay. I don't know why this side's always blurry. It's weird.
Well, that's a good point, Matthew. You could have a dirty lens.
Yeah, I can. Oh, yeah. You know, right? That's a good point. Hold on a second. I actually have a lens cleaner. I'm gonna. Let me turn the camera off for a second. Make a difference?
No.
I'm sorry?
Nope.
Okay.
Oh, well.
I tried. Sorry. Are there any questions on this problem? So one of your homework problem is basically this one. So I just wanted to get you started on it. Now the rest of it is just doing some algebra. Because you can solve this for z. Because once you write v in terms of the total current, because I sub c is the total current, then you can get z. And once you have z, once you have an expression for z, then it's just a matter of manipulating the equations. You can find phi, for example. You can find everything you need to know, actually. Okay? But I thought I'd get you started on this so that way you can complete the problem. And And again, all I use is some basic ideas that, the voltage across the inductor equals the voltage across the resistor, that the sum of the two currents through the resistor and the inductor has to be equal to I sub C. And I reasoned out that these two have to be perpendicular to each other, and that this one has to be first, and then this one second, because if I reverse it, then the current will not lag the voltage across the inductor if I do it the other way. Okay?
Professor, I have one quick question.
I'm sorry, I'm gonna come close to the computer to hear you. You said you had a question?
He did.
I'm sorry?
He did say that.
I'm sorry, I'm not. What was it that you said, Isaiah?
I was just making sure the at that top left equation, it's Vs squared equals Vr squared plus Vc squared. Is that minus or is that equals?
It's a minus.
Okay. Just making sure. Thank you.
This is a minus right here.
Yeah.
And this is an equal.
Thank you.
Okay. Let me do one more example. This one's in your notes. And usually I don't have time to do this problem, but we have a little bit of extra time. So I'll do it. Go back real quick. It's actually completely solved in your notes. I want to do one with a real inductor. I took this out of a textbook. This is a problem with a real inductor. And we want to calculate the resistance of the inductor in this problem. We want to calculate the actual power loss in the inductor and the inductance L. So let me set this up on the board. And again, the key to solving this problem is the phasor diagram. Okay, so we just have a basic circuit, 110 volts. We have an inductor, a real one. This is the real inductor. Now the voltage across the resistor is 50 volts. And the voltage across, so the voltage across the resistor is 50 volts. The voltage across the real inductor is 90 volts. So they're in series. And so I'm going to start by drawing my diagram. Just 1 second. Okay. Since these two are in series, the current through them is going to be the same. So I will draw I sub R. or just I in general. The voltage across this little resistance and this guy, they're parallel with that. Okay? How do I draw the voltage across the inductor? Well, the inductor voltage has two parts. The voltage across the inductor leads by 90 degrees. But there's also voltage across this thing. So this vector that I've drawn is the voltage across the real inductor. So this is the voltage across the real inductor. This is the voltage across the pure inductance. And this is V little r. But this is the actual voltage across the real thing. Does that make sense? Let me check the chat real quick. Okay, is there a so your question is there a linear circuit element with higher derivatives of current? No. The linear circuit elements are the resistor, the inductor, and the capacitor. That's it. The other elements tend to be active, like transistors, diodes, and you'll learn them in engineering 17. You'll learn about them then. Okay. So I have to add to it the voltage across the real resistor and then the voltage across the power supply is just this. Let me call this angle phi. Of course, this angle is phi. This is 50 volts. This is 90 volts. This is 110 volts. Can I figure out phi? What do I use to figure out phi? Law of cosines. So this, which is opposite phi, and I'm sorry I'm not writing the units in. And so we can figure out what phi is. And if you do the math, find my notes.
Professor?
Okay. You get 53.8 degrees.
I'm not sure if you can hear me very well, but is
I'm
there a
sorry?
reason? I said, is there a reason that the VS and the VR are squared next to the cosine?
These two?
No, the other two.
They shouldn't be squared, right?
No,
Oh,
you
these
put
are
VS
squared.
and VR.
Oh, yeah, you're right. There's no reason for it. I screwed up. Now, when you get the angle phi from the law of cosines, that phi represents the well, you're going to get an angle of that phi represents the angle between the two vectors. It means this. When you put them like this, the phi in the law of cosines is this. When you put them tail to tail, look, we don't have it that way, so the angle we want is 180 degrees minus that. And so we get 53.8. Okay, so we have, once we have the phasor diagram, once we have phi, the rest is pretty straightforward because the power loss is your current times V cosine phi. This is 110. How do I get the current? Well, in the problem, this is 50 ohms. If this is 50 ohms, and that's 50 volts, what's the current?
1 amp.
1 amp. When you work this through, you get 65 watts. Now, what does this power loss come from? It comes from the resistance. So what's little r? Well, let's see, this should be pretty easy math. 50 plus r equals 65. I'm sorry, 50 watts plus 1 amp squared times r equals 65. So the little resistance is 15 ohms. And then the inductance, how can we get the inductance?
We have phi. So our power factor cosine of phi would be total R over Z. Do we have Z?
Yeah, your total Z is going to be the square root of and we are at 60 hertz. I forgot to mention that. And so, yeah, you can do it that way, right? You can do it that way. But since this is 90 volts, and this is one amp, then Z is 90 ohm for the inductor. You can use this. And you'll get L is 0.235 henries. You can also figure out what this is, because all you got to do is take the 110 and multiply by the sine of 53.8, and you'll actually get the actual voltage across the pure inductance. Okay, the voltage across the pure inductance is going to be 110 sine of phi. So I have that problem completely solved in your notes, so you can take a look at it. Okay, I usually do that. I usually have it that way because this is I think the first time I've ever been able to actually do the problem in class. Okay. Okay, so the last thing then, if you guys have any questions?
Yeah, a quick one about the problem you just worked. We have, I have in my formula sheet, the cosine of phi is our power factor, which equals R over Z.
Yes.
Okay, so if I write that formula down and solve for Z, I get a different answer than is in the notes. Do you know why that might be? Unless I did something wrong.
This is your total Z, right?
Yeah. And the R on top, that would be the total R within the circuit, which would be, what do we call it?
65. Okay, I have to look into it and make sure I didn't make a calculation error then. So you use this and you got different values?
Got a Z of 110 ohms, and then the notes using your other method, it came to 90, I think.
Oh, but that's, I'm sorry, that's the Z of the inductor.
Oh, okay.
Yeah, and I probably should have wrote Z sub L. All right, that's the impedance of the total impedance of the inductor is 90.
All right.
And the fact that Z is 110 should make sense because there's 110 volts. I have 1 amp going through here, right?
Oh, yeah.
Okay. So I think what I want to do is introduce to you chapter 34. I'll be honest, it's my least favorite chapter in the course. Just give me a second.
Is it your least favorite because of our math limitations?
Yeah, I mean, I just got to like state a lot of stuff, right? I got to open up my PowerPoint slide. Hold on a second. Okay. I mean, there's some things that are interesting, but coming up with the equations is.
I see the word waves, and I was like, well, we can't do much with that.
Yeah. Okay, let me. Yeah, so chapter 34 is on waves, and it kind of really leads into what you're going to learn in in Physics 215 when you talk about optics. And we do have to do some hand waving here, actually quite a bit of hand waving here. It's because solving some of these problems, some of these equations are very difficult. And deriving things is very difficult. So you'll see me doing a lot more hand waving. And I'll try, if I have time next time, to actually do some problems where there's a problem I have where I look at the momentum of the wave. So if I have time for that, I'll do the problem. If not, I'll just tell you what the equations are. That's usually what I do. So chapter 34 is basically on waves. And it is a brief introduction. I want to start by writing down the four main equations that we've learned in this course. They're called Maxwell's equations. When Maxwell derived or came up with the idea of displacement current, that was a huge discovery. He was able to link the electric and magnetic fields together. And so we have four equations that pretty much summarize what you've learned in this course. Right? Gauss's law for electricity, Gauss's law for magnetism, Ampere's law, and then Faraday's law. If you add the Lorentz equation, basically those five equations, oops. Hold on a second. The blurriness is really bad. Anyway, when you look at those four equations plus the Lorentz equation, that pretty much summarizes everything we've learned in this course. I know it seems like we've learned a lot more than that, but those are the equations that summarize everything that we've learned in this course. And these are the fundamental equations. Okay? So Maxwell, once he came up with these equations, he started to work with them under various circumstances. One of the things, people don't give Maxwell enough credit. Einstein would say, would always reiterate how important Maxwell's contributions were to physics. Maxwell doesn't get enough publicity like Einstein, but if you think about it, his equations play a big role in our technology today, a huge role. He was able to manipulate these equations to predict the fact that there are electromagnetic waves that travel through space. These waves, we're talking about these waves. We're talking, for example, responsible for knowledge of this is responsible for example, our telecommunications, radio, TV, etc. And he was able to come up with equations that describe the properties of these waves. And one of the things he was able to come up with is the fact that the direction of travel of the wave is perpendicular to both the electric field and the magnetic field. So formally you can say that if the wave travels in the y hat direction, then y hat dotted with the electric field is 0, y hat dotted with the magnetic field is 0. And in fact, the direction of travel of the wave, the electric field, and the magnetic field form a right-handed coordinate system. Take the cross product of the direction of travel of the wave with the electric field, you get C times the magnetic field. And if you take the cross product of the direction of travel of the wave with the magnetic field, you get minus E over C. So that shows you the relationship between E and B. The magnitude of B is E over C. Okay.
Was C a constant? Just a
C is a constant. Yeah, let me say what C is. C is the speed of light in the medium. And we're basically dealing with vacuum, so this is the speed of light in a vacuum, so it's 3 times 10 to the 8th meters per second. In the medium, it's a little bit less because the light gets absorbed and re-emitted. He was also able to derive the equations governing the law of optics. Because before that, people would just build models to describe optical effects. His equations are able to derive all the optical principles. If you take 215, you'll learn, for example, that when light hits a surface, when light comes in at a surface, at an angle theta with respect to the normal to the surface, the angle of reflection equals the angle of incidence. You can use his equations to derive it. Okay. Before that, there were various models, and he put a lot of the optics on firm ground, on firm theoretical grounds. Now he also predicted that this guy, C, is 1 over the square root of mu naught epsilon naught in a vacuum. He predicted various properties of the wave, that they refract, that they bend when they go from one medium to the next, that they reflect, and the equations predict how they refract. The predictions predict how they reflect. So his equations allowed one to derive the laws of optics. And his equations were verified by Heinrich Hertz in experiments that were carried out a few years later. He also was able to predict that if you have an accelerated charged particle, it will emit electromagnetic radiation. So what are these waves? See, here's where I'm hand waving. I'm just telling you what the results are, right? What do these waves, what are some properties of these waves? And I'm going to focus on common waves that are periodic. And I'm going to look at waves that are far away from the source. They're called plane waves. I'll say some things about what the kind of waves when you're close to the source, but most of the problems we do, especially when you do optics, you assume you're far away from the source. So the source is periodic. It oscillates periodically, sinusoidally, and it produces a wave that varies sinusoidally with time. The wave is described by an electromagnetic field and a magnetic field. The electric field is perpendicular to the magnetic field. The electric field is in phase with the magnetic field, but their orientations are 90 degrees apart. As you see in that figure shows that the two fields are in phase, but their oscillations are 90 degrees apart. So here's some properties of the wave. I'm going to write down some more properties of the wave. If I plot E as a function of time, then the time it takes for the wave to go through one full cycle is the period. And then 1 over the period is a frequency. If I plot the electromagnetic field as a function of position, the distance the wave travels before it repeats itself is called the wavelength. What that means is each point, the distance the wave travels before a point on the wave has the same displacement relative to the x-axis. That's called the wavelength. And the period, the speed of the wave is just lambda over the period, and it's the speed of light. We can also write it as lambda times the frequency. We also define the angular frequency, omega, is 2 pi times the frequency. We also define the wave number as 2 pi over lambda. The amplitude of the wave is either E max or B max. It depends on whether you're describing the wave in terms of the electric field or the magnetic field. Usually in textbooks, we describe the wave in terms of the electric field and realize that the magnetic field is there too. The electric field, the magnetic field, and direction of travel form a right-handed coordinate system. I'm going to stop here, and then I'm going to talk about, on Wednesday, Maxwell's equations. What you see on the slide at the bottom is Maxwell's equations, one of them. Maxwell's wave equation, for a special case. And then we'll talk about the solutions to them. I'm not going to solve that. I'm just going to tell you what the answer is. Okay, this is where I'm doing a lot of hand waving. I'm going to assume that you're going to believe what I'm saying. Questions? Okay, then I'll see you on Wednesday. Like I said, actually and a lot of the stuff in chapter 34, a lot of the homework problems are plug and chug. You just have to know some basic things. I will on Wednesday do some problems that go a little bit beyond, because I want to talk about energy and a wave. You just need to understand it conceptually. What I'm
What day is
discussing.
that homework? I'm sorry. What day is that homework due?
That'll be due the Thursday before the exam. It's a little bit of a shorter assignment. There's a couple key problems you have to know how to solve. I'm going to do one of them on the board on Wednesday. So really, your responsibility is for some very basic stuff on the exam. All right, we'll see you on Wednesday.